Battery energy storage system is a technology that stores energy in the form of electricity using batteries. It plays a crucial role in managing power supply, enhancing the reliability of renewable energy sources, and reducing greenhouse gas emissions. A battery energy storage system BESS captures energy from renewable and non-renewable sources and stores it in rechargeable battery storage devices for later use. A battery is a direct current DC device, and when needed, the electrochemical energy is discharged from the battery to meet electrical demand to reduce any imbalance between energy demand and energy generation. The increase in renewable energy sources and the drive to achieve net zero carbon make BESS an essential technology for commercial and industrial organizations. By adopting BESS, it can provide a vital pathway in the transition to green energy and accelerate your journey towards net zero. BESS key aspects and types of batteries. Different types of batteries are used in BESS, each with its own advantages and disadvantages. Some of the commonly used ones are lead-acid batteries. Widely used due to their reliability and low cost, but they have a shorter lifespan and lower energy density. Nickel-cadmium and nickel-metal hydride batteries. These have a longer lifespan than lead-acid batteries, but they are more expensive and have environmental concerns. Lithium-ion batteries. They have a high energy density and long lifespan, making them ideal for BESS. However, they are more expensive. Sodium-sulfur and redox flow batteries. These are high-capacity batteries suitable for grid storage, but they have higher costs and specific installation requirements. How BESS works. BESS relies on one or more batteries to store energy, which can then be used at later time. These batteries may be charged using excess electricity generated by wind or solar farms, for example, or by grid connection during periods of low demand. Once the battery is full, it stores the electricity until it is needed. Battery energy storage systems offers more than just a standard battery. It is fully packed with technologies allowing its system to capture charge and execute discharge. The following are the typical technologies it includes. Inverters. Inverters are devices that transform direct current DC to alternating current AC. AC is the type of electricity used in homes and businesses. Control components. The control components of a BESS manage the charging and discharging of the batteries and regulate the flow of electricity to and from the grid. Integrated sensors. Integrated sensors monitor the BESS's performance and conditions, providing valuable data to help optimize its operation. Multiply battery modules. Multiple battery modules are composed of multiple batteries that work together to store and release energy. Functioning of BESS. A BESS charges up by drawing electricity either from the grid or from renewable energy sources like solar and wind. This stored energy can then be released back into the grid during peak demand times, thus ensuring a reliable power supply. Applications of BESS finds applications in various areas. Grid stability. It helps in maintaining the balance between supply and demand on the grid. Renewable integration. It enables the storage of excess energy produced by renewable sources for later use. Peak shaving. It can supply additional power during periods of high demand, reducing the need for peaker plants. Advantages. BESS can help in reducing greenhouse gas emissions, increasing the share of renewable energy, and improving the reliability of the power supply. It also has the potential to bring significant cost savings in the long run. Disadvantages. The main challenges with BESS are the high upfront costs, the need for advanced control systems, and the environmental concerns related to battery disposal. BESS is a promising technology that can play a pivotal role in the transition towards a more sustainable and reliable energy system. Battery energy storage systems application. BESS is used in a variety of applications, including peak shaving. Peak shaving reduces the peak electricity demand by using stored energy to meet part of the demand. This can help reduce the overall cost of electricity and the need for new power plants or upgrades to the existing grid. Microgrids. A microgrid is a small, independent power system that can operate either connected to or disconnected from the main grid. BESS can provide backup power for a microgrid in an outage and can also help stabilize the grid by providing energy during peak demand periods. Uninterruptible power supply. It is an electrical apparatus that supplies continuous power to critical loads during power outages. BESS is often used in conjunction with a UPS, as it can help ensure that critical equipment continues to function without interruption during a power outage. Types of BESS. There are various types of BESS available, depending on your needs and preferences. Some common types include lithium-ion batteries, lead-acid batteries, flow batteries, and flywheels. Each type has its advantages and disadvantages in performance, lifespan, cost, and other factors. Lithium-ion batteries. These batteries are one of the most popular types of BESS. They offer a high energy density and are relatively lightweight, making them easy to transport and install. Lead-acid batteries. Lead-acid batteries are another common type of BESS. They are typically cheaper than lithium-ion batteries, but have a shorter lifespan and are not as efficient. Flow batteries. Flow batteries are a newer type of BESS that offer a longer lifespan than traditional lead-acid or lithium-ion batteries. They work by storing energy in an electrolyte solution, which can be redirected to different parts of the battery as needed. Flywheels. Flywheels are another energy storage system that uses kinetic energy to store and release electricity. Flywheels are typically used for short-term storage applications, such as load leveling or backup power generation. How does a battery storage system work? BESS collects energy from renewable energy sources, such as wind and or solar panels, or from the electricity network and stores the energy using battery storage technology. The batteries discharge to release energy when necessary, such as during peak demands, power outages, or grid balancing. In addition to the batteries, BESS requires additional components that allow the system to be connected to an electrical network. A bidirectional inverter or power conversion system (PCS) is the main device that converts power between the DC battery terminals and the AC line voltage and allows for power to flow both ways to charge and discharge the battery. The other primary element of a BESS is an energy management system (EMS) to coordinate the control and operation of all components in the system. BESS power and energy ratings. For a battery energy storage system to be intelligently designed, both power in megawatt MW or kilowatt kW and energy in megawatt hour MWH or kilowatt hour ratings need to be specified. The power to energy ratio is normally higher in situations where a large amount of energy is required to be discharged within a short time period, such as within frequency regulation applications. For pricing purposes, however, the quoted measure is usually the energy rating. Advantages of BESS. There are several advantages to using BESS, including provide a cost-effective way to store excess energy generated by renewable sources like wind and solar farms. Can store excess electricity generated by renewable energy sources such as solar or wind farms, allowing it to be used at a later time when these sources are not available. BESS can provide backup power during outages or extreme weather events, reducing the need for costly distribution upgrades or emergency generators. Assist in load leveling and grid support, helping to balance fluctuations in electricity demand throughout the day and reduce congestion on the grid. BESS can improve power quality by smoothing out voltage fluctuations that may otherwise disrupt equipment operations. Many types of BESS are easy to install, making them a popular choice for businesses and homeowners looking for reliable energy storage systems. Disadvantages of BESS. While there are many benefits to using BESS, some potential drawbacks should be considered. These include higher upfront costs compared to other energy storage solutions. Issues with performance and lifespan are associated with certain types of BESS, such as lithium-ion batteries or flywheels. Increased need for maintenance and monitoring, especially if a qualified technician does not install the BESS. The reliability of BESS is typically lower than that of traditional power generation sources like fossil fuels or nuclear power plants. What is the battery C rate? A battery C rating is the rate at which a battery can be fully charged or discharged. For example, charging at a C rate of 1 C means that the battery is charged from 0 to 100% or discharged from 100 to 0% in 1 hour. A C rate higher than 1 C means a faster charge or discharge. For example, a 2 C rate is twice as fast 30 minutes to full charge or discharge. Likewise, a lower C rate means a slower charge or discharge. As an example, a C rate of 0.25 would mean a 4-hour charge or discharge. The formula is T is the time CR is C rate T equal 1 by CR to view in hours, or T equals 60 minutes by CR to view in minutes. Advantages of battery energy storage systems. Battery storage systems have several advantages when paired with renewable energy and non-renewable forms of generation. Solar and wind can be unpredictable, so battery storage systems are a key component in steadying energy flow by providing a steady supply whenever required, irrespective of weather conditions. Additionally, BESS can protect users from potential supply interruptions that could threaten the energy supply. Here are some of the benefits of battery storage systems. Environmental. Installing a battery energy storage system powered by renewable energy generation technologies helps reduce carbon emissions from fossil fuels and contributes to the net zero pathways in combating the effects of global warming. Reduce energy costs. BESS allows consumers to store low-cost solar energy and discharge it when the cost of electricity is expensive. In doing so, it allows businesses to avoid higher tariff charges, reduce operational costs, and save on their electricity bills. Reduce grid dependency. Battery storage systems guarantee a continuous energy supply, even at times when the network is unstable due to peaks in demand or extreme weather events. Always on supply. The sun is not always on. A battery storage system works round the clock and therefore compensates for any fluctuations in solar energy supply by storing any excess energy and maximize renewable energy generation. Enhanced resilience. A full battery energy storage system can provide backup power in the event of an outage, guaranteeing business continuity. Co-location of assets. Battery systems can co-locate solar photovoltaic, wind turbines, and gas generation technologies. In doing so, BESS co-location can maximize land use and improve efficiency, share infrastructure expenditure, balance generation intermittency, lower costs, and maximize the national grid and capacity. Frequency control. The battery energy storage system can regulate the frequency in the network by ensuring it is within an appropriate range. Discrepancies between generated and required energy can cause short-term problems, such as outages or blackouts, but BESS can quickly react and secure sub-second frequency response, stabilizing the network. Additionally, it guarantees voltage stability by keeping it within established boundaries. Battery storage can improve the reliability, availability, and efficiency of the power supply. BESS solutions can accelerate decentralized power station infrastructure, which can add value to commercial and utility-scale power generation models. Battery storage has no significant restriction on the geographical locations that it can be sited in. Storage technologies such as pumped hydro and compressed air are only suitable for a limited number of places. High energy density resulting in reduced footprint and fast response time greater than 150 milliseconds achievable. Battery energy storage system components. BESS solutions include these core components. Battery system or battery modules containing individual low-voltage battery cells arranged in racks within either a module or container enclosure. The battery cell converts chemical energy into electrical energy. The batteries are connected in series and parallel for the required capacity. Storage enclosure either as an outdoor module or containerized solution along with thermal management. Battery management system BMS, which ensures the battery cell's safe working operation, ensuring it operates within the correct charging and discharging parameters. In doing so, the BMS monitors the battery cell's current, voltage, and temperature and estimates its state of charge SOC and state of health to prevent safety risks and ensure reliable operation and performance. Inverter or a power conversion system PCS. The battery cell produces direct current DC, which the PCS converts into alternating current AC used for the power grid, commercial or industrial applications. Bidirectional inverters allow for the charging and discharging of the battery cell. Energy Management System EMS controls and monitors the energy flow of the BESS systems. The EMS coordinates the BMS, inverters, and other components of the battery energy system by collecting and analyzing data used to manage and optimize the overall system performance. Safety systems subject to system functionality and operating conditions. A BESS will include fire suppression, smoke detection, a temperature control system, and cooling, heating, and air conditioning systems. A dedicated monitoring and control system will ensure the safe operation of the BESS and the prevention of fire and hazardous incidents. The BESS will also be housed within a secure restricted access area and include CCTV monitoring. Principal BESS characteristics. Rated power capacity. Rated power capacity is the total discharge capability, usually in megawatts MW, or the maximum rate of discharge the BESS can achieve, starting from a fully charged state. Rated energy storage. Rated energy storage capacity is the total amount of stored energy in kilowatt-hour, or megawatt-hours MWH. Capacity expressed in ampere-hours, 100Ah12 V, for example. Storage duration. The amount of time storage can discharge at its power capacity before exhausting its battery energy storage capacity. For example, a battery with 1 megawatt of power capacity and 6 megawatt-hours of usable energy capacity will have a storage duration of 6 hours. Depth of discharge DOD. Depth of discharge DOD expresses the total amount of capacity that has been used. Cycle life, lifetime. The amount of time or cycles a battery storage system can provide regular charging and discharge before failure or significant degradation. Cycle life is the number of times a battery storage part can be charged and discharged before failure, often affected by depth of discharge DOD, for example, 1,000 cycles at a DOD of 80%. Self-discharge. Self-discharge occurs when the battery's stored charge or energy is reduced through internal chemical reactions or without being discharged from performing work for a customer or the grid. Self-discharge is usually expressed as a percentage of the charge lost over a certain period. It is an essential parameter in batteries intended for longer duration applications. Discharge rate. Discharge rate C describes the current that a battery can deliver for a period of time. As an example, C5 is the current a battery will provide over 5 hours to reach full discharge. State of charge. The state of charge is usually expressed as a percentage representing the battery's present charge level and ranges from wholly discharged to fully charged. The state of charge influences a battery's ability to provide energy or ancillary services to the network at any given time. The state of charge expresses the amount of capacity remaining. Round-trip efficiency. Round-trip efficiency is the ratio of energy charged to the battery to the energy discharged from the battery and is measured as a percentage. It can represent the battery system's total AC-AC or DC-DC efficiency, including losses from self-discharge and other electrical losses. In addition to the above battery characteristics, BESS have other features that describe its performance. Ramp rate. The ramp rate is the rate at which the BESS may decrease or increase its power output ramp down or up, respectively. Response time. The response time is when BESS must move from the idle state and start working at full power. Are slow to charge. Types of battery chemistries: lithium-ion, Li-ion lithium iron phosphate LFP, and lithium nickel manganese cobalt oxide NMC are the two most common and popular Li-ion battery chemistries for battery energy applications. Li-ion batteries are small, lightweight, and have a high capacity and energy density, requiring minimal maintenance and provide a long lifespan. Lithium-ion batteries can also be rapidly charged and have a low self-discharge rate. The disadvantages of this battery technology include excessive cost, inflammability, intolerance to extreme temperatures, overcharge, and overdischarge. Lead-acid PBA. Lead-acid batteries are well proven within the automotive industry and behind the meter grid and UPS applications. PBA batteries are widely available, low cost, widely recyclable, and can perform effectively at both hot and cold temperatures. However, due to advances in Li-ion battery technology, lead-acid batteries have a low energy density and sodium-sulfur NaS. A sodium-sulfur battery is a molten salt-based device. NaS batteries have several advantages, including high energy and power density, a long lifespan, and reliable operation under extreme 300 to 350 degrees Celsius temperatures. However, this battery technology is primarily suited to large-scale stationary grid storage applications due to high operating temperatures and corrosion sensitivity. Sodium is also a dangerous component because it is highly flammable and potentially explosive. Flow batteries. Flow batteries store energy in liquid electrolyte solutions, unlike traditional rechargeable battery solid electrode material. The vanadium redox battery VRB is the most prevalent flow battery type and is suitable for longer durations of up to 8 hours or where an extended lifetime is required. Despite their low energy capacity and charge-discharge rate, flow batteries respond quickly and reduce fire risk due to the non-flammable electrolytes used. Zinc-bromine, cerium-zinc. A zinc-bromine battery is a rechargeable battery that uses the reaction between bromine and zinc metal to produce an electric current with an electrolyte composed of an aqueous solution of zinc bromide. The zinc-bromine battery was developed as an alternative to lithium-ion batteries for stationary power applications from grid scale to domestic scale. The water-based electrolyte in zinc-bromine batteries makes the battery system less prone to fire and overheating than lithium-ion batteries. BESS applications. Battery energy storage can be beneficial for several reasons due to the flexibility of co-locating with other renewable energy sources or non-renewable sources. Battery energy storage also requires a relatively small footprint and is not constrained by geographical location. Let's consider the below applications and the challenges battery energy storage can solve. Peak shaving load management, energy demand management. A battery energy storage system can balance loads between on-peak and off-peak periods. The electricity demand fluctuates depending on the day of the week, time of day, and seasonality. As such, when there is peak electrical demand, prices are at their most expensive. Alternatively, the power price is at the standard rate when demand is low during off-peak periods. Peak shaving allows users with battery energy storage systems the assets to store power during off-peak periods and discharge during peak times to reduce electricity costs. Energy time shifting arbitrage. Energy time shifting or arbitrage allows users with BESS solutions to store their purchased power during off-peak times to use on-site when the imported power price is high. Alternatively, users can trade their stored electricity via the flexibility market's energy markets, ancillary services, and capacity market for income generation. Energy resilience. Battery energy storage can supply fast response backup power in the event of a mains failure to ensure infrastructure is operational and downtime is minimal. Using these battery energy storage systems alongside power generation technologies such as gas-fired, combined heat and power CHP, standby diesel generation, and UPS systems will provide increased resilience, mitigating a potential loss of operational costs, whilst protecting your brand. Frequency response. A BESS has a frequency response which allows it to provide active power output when there is a change in the electrical grid's frequency. A deviation from the nominal frequency indicates a mismatch between power supply and demand, which can destabilize the grid, causing outages or blackouts. To restore balance quickly, the BESS can adjust its active power output by reacting to deliver sub-second frequency response to stabilize and balance supply and demand within the network. The growing share of renewable generation and decentralized power plants connected to the network means battery storage will continue to play a critical role in our energy transition. Grid connected. In front-of-the-meter FTM applications, battery storage systems are typically referred to as utility or grid-scale battery storage and can be connected to transmission or distribution networks to reduce congestion management whilst also controlling voltage and providing reserve and ancillary services. A BESS can also support power generation assets. Commercial and industrial. BESS are typically behind-the-meter BTM, and applications include avoiding electricity network charges, benefiting from tariff differences, delivering value-added balancing services, or enhancing on-site resilience and energy consumption when paired with on-site solar PV, thus saving money and optimizing the sustainability benefits. Co-location. BESS can be paired with other renewable, and non-renewable technologies to form a hybrid power solution. For example, these hybrid systems can enhance the performance of new and existing gas engine installations. Combining a battery storage system with gas generation and solar power will go a long way to making cheaper, cleaner, and more reliable power more accessible. Why is energy storage needed? Most energy systems have a varying demand with some short-term but significant peak power requirements, which results in a capacity requirement which might only be used for a fraction of the time. Energy storage enables energy to be saved for later use. Energy storage creates capabilities and efficiencies low-cost energy for the electric grid and assists in mitigating climate change. Renewable energies are intermittent in nature, i.e., their capacities to produce energy vary with time. Energy storage from renewable energies can avoid any curtailment of renewable energies during favorable weather conditions when excess wind or solar energy gets generated. BESS alternatives on energy storage. Aside from battery energy storage systems, other energy storage technologies include pumped hydro. During periods of low electricity demand, surplus generation is used to pump water from a low elevation reservoir up to a high level elevation. When water is released from the high level elevation, it flows down through a turbine to generate electricity to meet peak demand. Compressed air. Electricity is used to compress ambient air, which is stored under pressure in underground caverns or containers. When electricity demand is high, the pressurized air is heated and released into an expansion turbine generator for power production. Flywheels. It is a way by which mechanical energy may be stored in the form of potential or kinetic energy. Electric motors accelerate a flywheel at high speeds through which the energy is stored as kinetic rotational energy. When there is an electricity demand, the spinning force of the flywheel is connected to a generator to produce power. Thermal energy. Electricity may produce thermal energy, which can be stored until needed. For example, electricity can be used to make chilled water during low demand and later used for cooling during peak electricity consumption. Heating demands vary with season and time of day, and thermal energy storage can load shift and smooth demand on the plant. Move heat from the summer to the winter.